So this is kind of our whole transmitter. All right, so far in the last module, you guys kind of talked about this block and this block. And of course, you've done some rudimentary amplifiers and buffers from before. So this is kind of a general idea of what our system should look like, right? But one thing we've not kind of simulated so far worked with is this MCU. Okay, so this is kind of a new aspect of how do you model this, right? Ideally, before we just said, okay, we have a 1 megahertz signal here, right? But we didn't really consider what all this looks like. End of the day, we know we need a buffer to make sure our MCU is not loaded. And we need to make sure that we have strong enough signal here, right? Because it's not a weak signal, why do we ever do that, right? So that's one important thing he looks for in this next module. And on the receiver, we can kind of see the exact opposite kind of a format. So it's just gonna radiate out. And we're gonna receive some signals here. Guess we could, let's exclude this for now. Okay, cool. So this front part, our front end, it's pretty much just a mirror image of this, effectively. I've excluded the LNA for the time being because we'll talk about that later, but this is very rudimentary approximation, right? So it's a 27 megahertz filter, 5 megahertz, 1 megahertz. Over here, you're 5, 27. This part's tricky, and so is that part, right? Why do we have this network here? And the reason for this is we need to sample our analog signals, convert to digital, right? We have ADC. ADCs have a certain range of values they can allow for, right? So what we have to do is make sure that whatever signal we put in, right, we want to have as much range as possible. For example, this is any signal here is going to be RF, right? It's not going to be any DC. There's going to be some DC offset, but our signal itself is going to be, you know, sinusoidal signal, no DC, and effectively, we want to make sure that when we put this signal into our MCU, this is the dynamic range of our MCU, from 3.3 volts to 0. If we have a signal centered here and has a large swing, what's going to happen is it's going to get cut off. So we lose dynamic range. So you're not going to see this at all, right? So we can go all the way up there, but you know we have no limitations here. But down here, we get cut off and lose dynamic range. So instead, we say, okay, if you want the maximum dynamic range, and this is something generally you can say, you know, I would be biased in the middle, 1.65 volts, which this resistor divider does. This capacitor helps decouple your AC from your DC, so you can set a new DC point here. And if these are the same resistor values, then you get 1.65 at that node, right? So now, if we have a signal coming in, it can be a small signal. We can choose to amplify it further, and we still maintain our dynamic range, right? So that's important. Any questions on that? Go So, there's gonna be a few things here that we're gonna talk about. If you remember from the mixer module, we modeled our MCU over there, and that buffer just has a 1 megahertz signal, right? So we fed in, we had our LO, 4 megahertz, and then we fed in some 1 megahertz signal, right? And this is what, 1 millivolt, and this was, we set around 0.7, 0.8 volts, right? So let me get some output. And if you were to look at this from the perspective of our actual diode ring mixer, so this is like our RF output. Right, and our IF is here, and assuming ground over here. This is our IF port here. You're effectively saying, okay, let's hook this up to some 1 megahertz source with a 50 ohm source resistance here, right? That's what we said. Problem is, as you guys encountered, these ports don't have very good isolation. In other words, we saw that you have LO leakage into your RF, IF leakage into your RF, but the opposite holds true. At the IF port, you'll see LO leakage here, and RF leakage as well. So you'll see over here, you had your 3 megahertz and your 5 megahertz. And these had some amplitude, right? Let's call it A for now. And then we had our LO amplitude, we can just call this VLO, right? And we saw that some of this is going to leak. So you're going to see some component of your 4 megahertz, 3 megahertz, 5 megahertz at some fractional amounts of these amplitudes show up here. And, well, why is that an issue? Well, if these components are too large, they can damage our MCU, right? We want to have our MCU be isolated, so we want to make sure that if there's any reflections or any leakage, that this is as isolated as possible from this. So what do? We put a buffer, right? That's kind of standard, makes some sense. So we're going to put a buffer here. That solves the isolation problem a bit more. However, if we have a very strong signal leakage, what happens to our system? The buffer doesn't do too much to isolate the two to make them independent. So we have to move to something called a T-attenuator. And as the name suggests, it's a type of attenuator. It's just going to shrink the magnitude of all our signals that go into it. So it's not a frequency dependent attenuator. Effectively, a resistor is an attenuator, right? So that gives us some basis there as to how we can implement it. Another nuanced thing is just like how on the receiver, we need a certain amount of dynamic range that we would like to maintain. Over here in the transmitter, we can have a DC bias, 1.65 volts, right? We can have a certain amplitude signal, but we're not going to send a really small amplitude signal out from our transmitter, from our MCU here. That'd be a waste, right? Why send out a small signal and then have to amplify it more over there? We can make it larger here, and that our front end has to do less work to transmit it. So for MCU, ideally, there's 1.65 volts. We have something that goes between 0 and 3.3. The problem with this is it's a pretty large signal. All of these are small signal quantities, and that's how we've modeled all of it so far. So you can probably imagine that you have this very large signal now going into, we hook it up directly without the buffer, without the attenuator, into our mixer. And the problem with that is it's going to make our mixer nonlinear. And this is important because modern day mixers, the way we view them is from the LO port, it is nonlinear. From the IF port, it is linear. If this signal is too strong at the IF port, we can no longer view it as a linear network, which means that we're now going to get more harmonic distortion. All right, and these are kind of complicated words. You'll probably see these later, but generally, if the system is linear, you put one frequency, you'll get one frequency out. The more nonlinear it is, the stronger the harmonics of it will be. All right, so the best way you can think about this is, I'm going to write this here. Any system can be modeled like this. All right? So you have some system, put in some X, and get some Y. All right? What's this? So if x is pretty small, this x squared term is small, this x cubed term is small, this x bar n term is small, right? So our system effectively just becomes y is equal to alpha 1 to x. This is a linear system. This is our small signal model, right? If x is pretty large, now we're going to see x and x squared and x cubed. And if you think about what x is going to be, you know, it's e to j omega t, so omega naught t. So x squared is going to result in e to the j 2 omega naught t. So you can see that we get your fundamental, second harmonic, third harmonic, nth harmonic, all right? Now, all systems are inherently nonlinear, right? You can never get a purely linear system because you can never get fully rid of these components, but it's small enough and you can approximate it, right? But if these harmonics are large, we start to see them. If your x is large, start to see these other higher order terms. For a mixer, this is problematic, right? Because for 1 megahertz, we saw that we're going to get 3 and 5, then we're going to get 1 mixed with second harmonic of your LO, then the third harmonic. You're also going to have intermixing. So just from 1 megahertz going in, we have a lot of output spectrum across very large bandwidth. Now, if this signal is large, we're going to have 1 megahertz, 2 megahertz, 3 megahertz, so forth, going into our mixer. And you can imagine now that it's going to create a lot more, it's going to be harder to discern our different amplitudes. Things are going to overlap, going to get more of a, I wouldn't say use the word noisier spectrum, but it's not going to be as clean. We're not going to see just a 3 and a 5, right? So that's an issue. So we want to make sure whatever signal we put in the 1 megahertz, and our mixer operates as linearly from this IF port as possible. That's a really large signal. We can't do that. So what do? We attenuate it a little bit. Okay. So what's going to happen is we're going to shove an attenuator here. That's going to weaken it a decent bit and also help take care of isolation. And that way, whatever signal we see here isn't as large. You may ask, well, okay, if it's going to attenuate anyway, why even have a large signal to begin with? The reason for this is the way the DAC works on the board is we only have so much control and precision over it, and it's much easier to have it have larger kind of rail-to-rail swings just based on our digital encoding. This is a way to have better mixer performance, and if you want, you can go through in this next module. You'll have to replicate your MCU as, you know, something at 1.65 volts amplitude. You'll see that if you insert this buffer, you insert the T attenuator, you'll get better performance at the output. So that's something you can explore. So, now that we've talked about this, any questions on any of that? Cool. Some of these concepts about, you know, harmonics and linearity, we'll touch on in RAP. We've touched on a little bit. It's not explicitly part of the curriculum. It's something you'll touch on more in further courses, but it's nice to get exposed to these concepts because understanding how things evolve in the frequency domain is very important when you characterize the system. So maybe you'll touch on this in 163A or 215A, 215C, but you'll see it eventually. And I think it's nice to kind of get some, I guess, high-level exposure to why we care about nonlinearity. So, next thing we're going to talk about is the T attenuator. Or we'll give it the full name, the T-pad attenuator. So Benji, let me know when, you know, time is a concern. I have my phone too, but yeah.
It's only been 17 minutes.
Okay, we're good. I would like to be out of here, what is it, 6:40?
6:45 latest.
Like yeah. All right. This is a second point that I'm not brought up yet. Okay. I'm just going to write it out first. is going to be a bit more of an involved concept. I'm going to take a little detour to describe this phenomena. And this is another reason why we use a t-pad attenuator. So when we talk about components, we like to also talk about their noise. How much noise do they have to their system? End of the day, we want to transmit a signal and receive it. But if our signal looks like this in the frequency domain, so say this is like F, this is your noise floor. Our signal is pretty high above the noise floor. So you know what? Signal's pretty high above the noise floor at the receiver. Hey, you can pick it out and you can actually extract information out of it, meaningful information. Our signal is kind of really close to noise, to the noise floor. It's a lot harder to pick it out, right? So this is something we care about. We care about how much our signal looks compared to our noise floor. Signal to noise ratio, right? And what we see, sorry, were you writing that down? You got it? Cool. All right. What we see is that a lot of our components are noisy. All components are noisy in real life. Resistors are pretty noisy, but end of the day, we have to deal with that. Now we can start to characterize the noise of different blocks. So, amplifiers, how much noise do they contribute to our overall signal to noise ratio, our buffers, etc. And qualitatively, we can reason that mixers produce a lot more noise than standard blocks. Okay, I'm not going to go into the math there, but if you'd like, you can ask me later. I can show you that little derivation. But mixers produce a lot more noise than other blocks. Okay, so part of the reason we'll talk about low noise amplifiers later on the receiver is to make sure we set a good noise floor. We want to make sure that the first element in the series contributes as little noise as possible, because our overall signal to noise ratio is limited by that first stage. Okay, so we'll get to that eventually. But for now, even on transmitter, we still do care about noise. Okay, on both transmitter and receiver, more so the receiver. So mixers generate a lot of noise passively. You can think of diodes, right? That compose our diode rate mixer. They have regeneration and generation and recombination of carriers. Carriers are going to be a noisy, Fermi process, right? They have some distribution, right? And of course, when you have carriers moving around, that's thermal energy, that's thermal noise. You can refer to that as Brownian noise or white noise, however you would like. Effectively, it's the same thing, but there's noise. Mixers are noisy. It's kind of the general point. So we want to try and attenuate this noise, and attenuate, t-pad attenuator. It's another reason. Okay. So what we're going to do now is talk about how to make a t-pad attenuator. The next things we're going to talk about, I'm going to give you guys a calculator for. So you just plug in whatever spec you'd like. It's going to spit out the values. Is it important to know these general derivations? Not really. I think it's kind of cool. No one's going to ever ask you this on an interview, but it's cool to be aware of how these things work. Right? So it's a bit of a review of 2 ports as well. So our t-pad attenuator looks like, you can tell it's a T, right? Hence the name. And let's try and figure out force or termination, right? Let's say we put this t-pad attenuator before a filter. The filter ideally looks like 50 ohms, and it expects 50 ohms. So that's some termination, right? And we hook it up to some source, and we want to figure out what impedance we see looking at, okay? So we can do a few things. We're going to write a few equations out here. And it's going to be a bit of algebra, but hopefully it's not too bad. And the end result you'll just see that you should keep track of is the dependence of your input impedance on these values and this. So this is one equation, and you can kind of see how this develops, right? We have your, you have your R2 in parallel with your R1 plus Z0 this way, and then you effectively have a voltage divider between that and that R1, okay? And then that's gonna get multiplied by another voltage division ratio here to get your V out, right? So this voltage here is at this node, and then V out is going to be here, which gives you this factor there. Okay. From here, we can calculate what our gain is from V in to V out, which is V out over V in. Okay, and now we want to do impedance matching now. At the end of the day, we shove an attenuator in there, we want to make sure that we still can maintain maximum power transfer. Okay. So to do that, let's see what's the best. I'm gonna write it up here. 1 plus this hopefully makes some sense, right? R1 plus R2 in parallel with R1 plus Z0. Okay. And now from here we can say that we get this equation. And if we plug this in over here, this term, this, so that our gain is equal to Z0 minus R1 over Z0 times Z0 over R1 plus Z0. Okay, so get this for our gain. So that our gain is effectively independent of R2. Okay. Now if we want, we can solve for R1. And plug R1 back into this expression and solve for R2. And we get this. And in general, and this is just the inverse of gain, right? The inverse of gain, attenuation. So what we can say is that our attenuation in dB and this is going to be voltage quantities. You can also just write this as 20 log base 10 of 1/8. Okay. Any questions on this? So what's going to happen here is effectively in the module, it's going to ask you put everything together without the buffer, without the T-pad attenuator, and without the next thing we're going to talk about, which is an LC matching network. Look at the output of your system. It should be pretty bad, pretty messy. try inserting these things in one at a time and seeing how your performance improves, okay? And you may think initially it's kind of weird, okay, we're putting in an element that has no frequency dependence, these are all resistors, and yet we're going to get better frequency performance in our spectral domain, right? That might be weird, but again, it just ties back to this whole concept of harmonics. Okay. Just be aware of that. The other thing is that, again, there's going to be two links in there. There's going to be some calculators that'll tell you what values you need given a certain attenuation and a certain termination. That way, all you have to do is figure out where do you put these things, which we tell you. The values, the calculator tells you. After that, all you have to do is kind of click run. And just keep note of how your system changes. And I will say what we did last year is we had various groups. Everyone would put their modules before that they made together. We would all test it and we'd pick the best blocks from each group and put that into one design. This year we're not doing that, partly because of time and partly just because it's a bit more inefficient. I think it's more impactful to have a good design and you guys mess around with your stuff, and that way you can compare to a reference, and if it ends up being better, great. But then this way, you know, you can mess around on your own time and kind of see how these things improve the system, and you have an actual guideline of performance without just saying, okay, it gets better, but better in reference to what, right? So it always helps to have some guideline of what you're aiming for, apart from just better performance. And that's something I'm going to touch on at the end of this lecture and give you some more numbers that we expect to see to characterize our transmitter and receiver. All right. The next thing we talk about is impedance matching. I expect this to maybe take 20 minutes, so I think it's fine. Yeah. Let's see. Alex, you got this, right? Did I erase this material, Alex? So, next thing, impedance matching. For those of you who have done 101A, hopefully this will be familiar. We're not going to use a Smith chart in this lecture. The plan was to, and then I figured that it'd be better to move to the next lecture where we talk about more 101A related content. That way it's a bit more of a flow. Because otherwise, I'm going to be going through all the details of doing the math out and then putting a Smith chart in there, and it won't really do anything for this lecture as far as the conceptual understanding. But having it in the next lecture, I feel like we'll have the content a bit more paced correctly. So that way, I don't have to toss in how's the Smith chart work over here and confuse you guys more. This lecture is a bit more of an overview. That's kind of the goal of the whole system. So as the name suggests, we want to do impedance matching, presumably for maximum power transfer, conjugate matching, and we want to use 1000. So let's do a few hypothetical scenarios here. We have two scenarios here. This is scenario 1. Scenario 2.
Just a quick question.
Yeah.
An attenuator, that doesn't affect the common mode, right?
This It does. I'll erase it. But effectively, ideally in your system throughout the RF chain, you have DC blocking capacitors for your amplifiers, such that in the signal path it is purely RF. In reality, you're going to see some DC level due to LO leakage, DC offset, various other offsets. In reality, yeah, you may have DC offsets here, but in general, because you end up having some DC current, then you will have slight deviation, but hopefully very small. And you take enough precaution in your system to make sure that everything in the signal path, there's no DC. You have decoupling capacitors.
And what this circuit does is compresses the amplitude, right?
Yeah. You can think of it as like a fancy voltage divider, effectively. It basically is a voltage divider. You can think of it like that. All right, you have a division either here, there. Okay. So, first scenario, the real part of our load is going to be greater than that characteristic impedance there, Z naught. The second part is that RL is less than Z naught. And this is a bit weird to think about because when you think of Z naught, it's like square root of L over C, so it's not like there's a value and it's like imaginary, but also not. But think of the number is all 50 ohms. When you think about these two scenarios, it gets a bit weird to think about in terms of Z naught being imaginary, even though if it's imaginary, there's no real component. But this is like 50 ohms in a system. Make sure the real part of your load is less than or greater than that. Slightly tricky notation there, but the process is very similar between the two. So, I'm gonna write a few equations out here. And I guess to help guide the thing I just said. This holds for both cases, okay? So, case one. This is gonna be a lot of math. Don't expect any of you to know it. It's in Posar if you really care about going through this and other details. We have a smooth chart for this stuff, so we wouldn't have to do it, but that's the next lecture. For now, I would just like to show you guys how much grunt work it takes to go through all of this. And next lecture, seeing the Smith chart will hopefully make you go, okay, that's one really useful application of the Smith chart. And Smith charts are super useful. I think for any RF interview, it's like the first thing they ask is, have you seen the Smith chart? And if you say yes, then all your interview questions from then on will be Smith charts. If you say no, good luck. Okay. So Smith charts are super important, and we'll get to the next lecture. Hopefully this makes some sense here, this equation here, right? Your JX for scenario one, it's gonna be in series, all right, it's gonna be parallel. The assumption here, sorry, I'll just clarify. Let's do something here. You guys know you can call a resistor R, right? You can also describe it as conductance, and use capital G. It makes more sense to talking about looking at things in parallel, say a parallel resonant sync, instead of having an R, you just write G. And this way, when you put things in parallel, you just add them together. It's nice and easy. That's what this B stands for. It's effectively saying, let's take an inductor, right, which has a positive relationship with frequency, and take its quote unquote conductance effectively, and saying let's put it here. So we have something like that in parallel with the ZL here. We're gonna have just 1 over that thing, JB. I think what the B stands for, but
Susceptance?
Susceptance?
Yeah,
Susceptance?
susceptance.
Yeah,
I can't remember.
Sus-
I don't know why it's a B, but yeah.
Yeah, that always is, yeah, susceptance, so, it's a little saucy vodka. Okay, that's the easiest. That's what the B stands for, saucy vodka, alright. So, that's the B, and then you just put this one over ZL, right? And it kind of simplifies. So, and then of course you want to speak of your characteristic impedance, ZL. That's one equation. And now we're gonna write a few more out. And these two are effectively just matching the real and imaginary parts. When you go through this math, do it all out, and make sure imaginary is on both sides, the coefficients are the same, so you get this relationship, and then real parts get this one. So from here, now solve for B, our little susceptance. I'm not gonna call it saucy vodka anymore. Don't ever quote me on that.
We have it on record though.
That's fine. That's fine. Don't quote me on it. I'm gonna blame AI for that recording.
There's a deep fake.
There's a deep fake. Someone went through all the effort just to get me to say saucy vodka on a rap recording. Hilarious.
The more you say, the more it's gonna be recorded.
I'm not saying anything. It's the AI. Alright. This over. Okay. So this is one set. It corresponds to scenario one. If x is greater than 0, it's going to be an inductor. B is greater than 0, it's going to be a capacitor. And then conjugate's case of this. Cool. So what this is telling you is, hey, if you have a certain system and you want to impedance match it, you have a Z naught and a ZL, you will pick your B and X values correspondingly. Kind of complicated, as you can see. But the good part about this is, you know, like I said, if you know your characteristic impedance, you know your load. You can discretely solve for these two and from their signs figure out what element you need. Okay? And this is kind of important. We'll see that this in contrast to scenario 2. A lot of the times we prefer to work with capacitors just because inductors tend to be more expensive. So whether this is for IC stuff, which you won't ever really do impedance matching like this, or more from an RF microwave perspective, whenever you can get away with using a capacitor over an inductor, it's just better, you know, because they have a bit more parasitics to them to deal with more of a resistive loss. With capacitors, you don't really care. The quality factor you do care about, but not as much for an inductor. So this is scenario 1, and we're going to see how scenario 2 compares to all of this. Any questions on this? I mean, it looks a little scary, but you just have to make sure your real and imaginary parts correspond. And then from there, just doing a bunch of algebra, which no one really likes to do, but fortunately you can't avoid it. I think you guys are gonna find the next thing I talk about more interesting though, after scenario 2, but yeah. Scenario 2, on the other hand, goes as follows. we are trying to get the perspective of Zn and Jx, right? So here, this is in series. So you start off like this. Scenario 2, it's in parallel, so you're gonna have like a parallel representation, right? Again, this is all in Posar if you would like to open it. Or I think even in some network theory books they'll cover this. Actually, I don't think they'll cover the impedance matching network theory. Posar has this for sure. This and a lot more. Okay, and again, this still holds here for these. But you can see that now we have this like plus, it's not the same plus minus. Over there, that just became a 1 over b plus and minus the 1 over BRL. So what you do is you're gonna go through, do this math in like both scenarios, right? I'm not saying you guys for the module, but in general. You'll do this and you'll see what values of b and x you get for these two scenarios. And you want to use the one that has more capacitors, just for cost primarily. But this is like the design, that's how the kind of cost manifests itself from the math. Okay, any questions on this? Again, same kind of derivation there. That's the real and imaginary. Now you can simplify all this and use a Smith chart. That's for next lecture. Now, where would we use these type of impedance matching networks as opposed to a T-pad attenuator? Well, let's just say we have a very simple scenario. Right, let's say we have the first scenario. Some inductor and some capacitor. And let's say I have some RL. Right, this looks kind of like a filter, right? Well, the great part about this is, yeah, it acts as a filter. You also get impedance matching at a particular frequency. That's the important part, at a particular frequency. The T-pad attenuator guarantees operation across all frequencies. Well, let's go to break the resistors, but you know, it guarantees impedance matching across a very wide band. Trade-off is you have attenuation constantly. Ideally here, your signal will be slightly attenuated at these frequencies, but it's going to go through more or less unimpeded and impedance matched. As you stray away from these frequencies, what you're going to see is you don't have, you know, conjugate matching anymore. And if you remember from, I guess, circuits, you get something that looks like this. Right, maximum power transfer occurs when these two R's are equal. Right, and if you look at the curve, you can something that looks like this. Right, maximum only here when R1 and R2 are equal. Right, but if you stray away, power transfer goes down. So effectively, as you go away from this resonant frequency there, conjugate match is changing, and other signals get attenuated. That's kind of useful. So you have both the properties of a filter and a matching network. Now, the downside is when you make a filter, you can choose any values to get a certain cutoff frequency. Here, the values you choose are dictated by conjugate matching. And the filtering is not so much a frequency response due to that as much as it's due to just this ratio here. Effectively, you get good characteristics from this. Now the cons, again, If you have an inductor, it's probably a bit more expensive, but generally, you go between a mix of this and the T-pad attenuator based on application. Any questions on that? In rap, we primarily use the T-pad attenuators just because getting stable enough inductor values is a bit annoying. Yeah.
Wait, how are we using the T-pad attenuator as an impedance matching network?
Yeah, so I'll erase it, but let's see. Okay. So flip that equation again. First thing we said was, we had our general like A equation, right? Which was 2 parallel with R1. No, it's not, sorry. Something like that, right, yeah. And then for impedance matching, we pretty much wanted, whatever impedance you see here, right? That's going to be 1 plus R2 parallel with R1 plus Z0. Z0. This is our impedance matching criteria. So by forcing, this is always going to be present for our gain. By forcing this condition, we can solve for now the values of R1 and R2 that ensure this is met.
Is there a reason why we're using T-pad attenuators instead of pi attenuators, or like?
It doesn't really matter.
It doesn't matter, yeah.
It doesn't really matter. I mean, I think the math is a bit more digestible for a T-pad attenuator, and I think pi attenuators can give you a bit more attenuation. I could be wrong, but for all intents and purposes, it's practically the same. Yeah. I think pi does use slightly higher attenuation. I could be wrong. I think Poser talks about that somewhere in there. I think the calculator also has a section for pi that could generate both T and pi. You can compare and contrast the two. Alright, so next thing that I think is going to be the most interesting thing all of you are going to see, which relates back to our favorite thing, which is amplifiers. I feel like people really like amplifiers. Oscillators kind of boring. Amplifiers, oh cool, we get to amplify something. So we're going to go back to amplifiers now for a little bit, and we're going to stick to amplifiers even for next lecture. It may not be very clear why, because we're going to cover the next lecture related to amplifiers, but I'm going to try and make them relate as closely as possible. We'll give you all a heads up. I know, Mateo, you have a MacBook. Alex, do you have a MacBook or no?
I do have one.
Okay, anyone else have a MacBook? You? That's 3. Anyone else here? Okay, cool. Ideally, I want to get us all ADS licenses, which I don't know how well it works on Mac, if at all, unfortunately, but there is a DAV laptop.
Do we need it to be a laptop, or can it be a machine? I do have a Windows machine.
Oh yeah, that's fine then. Yeah.
Same.
Yeah.
You can get ADS by just using like Chewy Wong email.
Yeah, I was gonna use like Professor Wang's email. That's what I've been using. But yeah, ideally, for next module, I'll have to make the next module. Next lecture, we're gonna talk about S-parameter stuff, and I feel like using software both give us exposure to actual industry tools and also helps see what's going on. So doing all of it by hand is gonna really suck. All right. So ideally for the next one, I want to get you guys an access to ADS. So yeah, it helps that okay, you guys have the means of accessing like a Windows computer. It makes it easier. And doing S-parameter stuff by hand is a bit of a pain, but ADS way simpler. And that way we can actually get to see some of the theory be applied in a more direct manner. That's for next time. But okay, good to know that you guys have a means of accessing or have a computer that can support ADS. Alright, so back to amplifiers. I'm gonna erase this. This is gonna be a sneak peek into general amplifier topology we use in the next lecture. It's not gonna be the exact same, but most of it will be parallel. talk about the common emitter with an LC tank. A few of you might have seen this before. It's something that you don't really cover from like 115A or 115B, just kind of stumble across it. Or if you have a BD for 115A, you'll talk about this. So there's that. So I guess more specific, tank slash resonator. Some people care about terminology, so resonator might be more appropriate. First, let's talk about, we have some network. It looks like this. How could we convert this from a series format to a parallel format? Right, some of you might have seen, like if we have a series RLC tank, how do we convert that to a parallel RLC tank? Kind of the same idea here, right? How do we go from series to parallel? So ideally, RS transforms in some resistance, call it RP, and this XS also transforms to some impedance, call that XP. And now if we just do a bunch of KCL, KVL, we can hopefully get a meaningful relationship out between how these values correspond to these ones, such that this ZS is the same. Okay. So this is going to be, let's call this equation 1, and call this equation 2. So what's going on here is, you have imaginary term in the numerator, and we're going to use multiply by conjugate here and there, so we get a real and imaginary. Hopefully that's clear. Next step is we're going to define a few things. So we're going to call it Q, not the orbital Q. QS is going to be XS R over RS, and in general, this can just be this imaginary part, any network, or the real part. Any network, this relationship will be useful. A lot of your classes, so if you see that, you can just kind of remember imaginary over real. And we can do the same thing over here, and we could say UP is equal to RP or XP. Now we have a few equations we can work with. So we set the equations 1 and 2 equal, because ideally they should be. The ZP, by the way, sorry, call this ZP. We end up setting them equal anyway, but just for the sake of being consistent, that's ZP. So we set the equations 1 and 2 equal. What can we say? We get this. And QS for the QP. And get these from setting 1 and 2 equal, and what's gonna actually end up happening is initially this is going to be QS squared and QS squared over here. QP and QS are the same because, in effect, these two networks are the same. So the energy stored and dissipated, stored in the electric field and dissipated through the resistor, in the case of capacitor, right? That's gonna be the same. So we can say QS equals QP. It wouldn't make sense if they weren't the same, right? So this kind of follows directly from the fact that those two networks are identical. Okay. So this is a useful relationship, and let's see how this translates into common emitter. Okay, we're actually really good on time. I think this next part should take like 15 minutes, so we get to go early. Let's go back to our basic amplifier. Okay. L, call C2, RC. Okay, this is our basic common emitter amplifier with emitter degeneration and a bypass cap, and R1 and R2. There's RE here for a better beta and temperature stability. Any questions on that? It kind of looks familiar. Now, we said before that let's assume at our frequency of interest, our signal bypasses this RE and goes down there. So we effectively have no emitter degeneration. Our gain, in that case, is going to be effectively, let's just ignore this branch for now. Oh, we can say, yeah, let's just say C2 is also a short at that frequency. Right, so at our frequency, this gets bypassed, C2 is also a short. So we're going to get an R0 in parallel with RC, in parallel with RL, okay? And we surmised that the highest gain we can get, this is a parallel function, that if we make RC infinity, RL infinity, the highest gain we get, negative GM R0. Can't really bypass this value, ever. By definition, we can't bypass it. So what do we do to try and get our RC and RL to infinity? If we get that to infinity, we have to maximize our gain. Seems like a pretty good idea, right? So let's try and think about a few concepts here. Well, I have something that looks like this. At resonance, what does this look like? Anyone remember? From 110 or something like that. That's 110, right? Yeah. Any thoughts?
The reactances cancel out.
Yeah.
So yeah, it's short.
Looks like a short, yeah. This looks like 0. And we make these parallel. That's not an inductor. Same scenario, same resonance frequency.
Open circuit.
Looks like an open circuit, right? So, infinity. Okay, so we get an infinite impedance. So ideally, we want to insert some network up here, such that when looking into it, infinite impedance. That way, this term goes to infinity, and all we're left with is R0. Seems kind of straightforward in theory, but how do we do that? We have to be kind of careful. From this, you can kind of reason, hey, we want to shove an inductor and capacitor in there somehow. But we have to be careful with that, because we have some other capacitors there, right? You have that C2 that we want to be careful of. So how do we do this? And I'm gonna draw out the general topology for you. On this side, you take it from there.
Excuse me.
And I'm just going to ignore, well, I'll draw it out. This part doesn't really do anything for biasing anyway, so you can practically just ignore it and move on. Same as before. Your RE and CE are still here, because you still want this phenomena to take place where at a frequency of interest, RE gets bypassed. What we're gonna do instead, so you can drop it there, call that L, call that C, and we'll just call this RL. Keep that standard. So this is what our kind of new and improved topology looks like, but let's actually go through it and see how it operates and see if it, acts as intended. And first step is let's make a small signal model. After all, this is a small signal gain, so verify it like a small signal model. So we do this, and this is something that I think everyone takes for granted when making the small signal model, but these resistors are still there in a small signal model. We just assume them to be so large that we don't see them. And sometimes they do come into play. Very rarely, but we do care about it nonetheless. We're going to assume that at this frequency of interest we're doing a small signal model at, that CE is bypassed, in which case the emitter, this looks like it's being tied directly to ground. Like that. As usual, we'll just add the current source, which is V pi, GM pi, and of course, all of this stuff, right? What does that look like? So, I'm gonna make a modification here, call this RLS. And although I just erased it, this, if we look up into the collector, it looks like we have an inductor, and parallel, we put a capacitor, some resistance. We want to ideally transform this into something that looks like this. And that way, the inductor can sit right there, and we just have a parallel RLC tank. Luckily, we discovered how to do that, right? So we call that RLS, okay? Then we can get the following here. And let's call this, call that C for now, we'll call this CP. And the relationship I wrote before, let's see where is it? This relationship, right? Yeah. Let's assume we have a pretty high quality factor, we use good enough components that have a good quality, higher quality factor. And from here we can surmise that RP is going to be decently larger than RS, right? So if Q is on, let's say what's a good Q value, we used, what, 20 to 30 before, right? So for our oscillators, so Q is 20 to 30, even like 10, the RP is like 100 times larger than RS. So we can reasonably assume this is going to be much larger than RS. That's our first assumption. Next step is, this looks like, put that there. This looks like an, parallel RLC tank. It's gonna resonate at some frequency. We're assuming the BJT has no capacitances here. In reality it does, but it's gonna be really insignificant compared to this DC block of cap anyway. So next step is, this forms an LC tank. This dictates our resonant frequency from this formula. So now we designed this tank to operate at our frequency of interest. So we make an amplifier 1 megahertz. We make sure that there's a mega naught is 1 megahertz times 2 pi, and figure out what LMC values we need. If we want it at 5 megahertz, again, do the same approach. So you'll see it's kind of the same idea here as designing the CE value, right? Make that certain value such that at that frequency, that impedance is 10 times less than RE, at which point most of your signal will steer towards CE. Kind of the same concept here. Again, it's a frequency dependent derivation of the values. So that's the important part. So you can probably surmise that this frequency changes by 10 times, these values can be quite different. Okay. Whatever that would be, 100 times. Yeah. L would change by 100, or CPU would change by 100, or a combination of 10 and 10. So, if we say this resonates at F naught, what happens? Well, all we're left with, and I suppose I should draw this here, it's a good old early effect that we can never leave behind. If this looks like infinity, this LC at F naught looks like infinity, then effectively we have this infinity in parallel with this RLP, which just leaves RLP. Then this RLP will show up in parallel with this R naught. Now ideally, if we can make Q infinite, then this also goes to infinity, in which case we just see R naught. But Q cannot be infinite. Any reasonable component we're gonna have loss. And you may think, okay, that loss we can just ignore it. Yeah, sure, but then, of course, any loss is going to be that going to cause certain resistance, RLP. It'll be in parallel with R naught, and the parallel operation is not like a linear operation. So even though the RLP might be really large, 100,000, that's going to be in parallel with R naught. So it's not a direct translation, you have to be careful of that. And if we do all of this out, ideally our gain is negative GM R naught parallel with RLP. Now, let's talk about a few things here. Okay, you may say, well, we still have R naught in parallel with something, so, why couldn't we just make RC infinity? Anyone tell me why? Can't just make RC super large? Yeah.
You're gonna get, R naught's gonna always cause it to decrease.
That, yeah, but in terms of biasing, right?
Oh,
If
then if you
yeah.
draw any type of current, you're gonna immediately
Yeah.
drop all the voltage across, per se.
Exactly, yeah. Remember that we need VCE to be at least 0.2 volts for it to be in forward active region. And hey, if it's RC super large, we have 1 milliamp. 1 milliamp times 100 ohms, 1,000 ohms, it's only 1 volt. Make RC larger, kind of see what happens. So that's one area we can't really mess around with too much. We need good biasing, right? Now let's take a step back and think, what happens here? This inductor is gonna have some parasitic loss, whatever, right? But you can model that loss as a resistor in parallel here. And we call it R para for now, R parasitic. I wouldn't even say it's parasitic, it might be the best way to describe it. But the idea is this inductor for DC will sustain no voltage drop across it. It can, right? This means that this is VCC, our collector is at VCC. Which means as far as making sure our collector is high enough above the emitter, that's gonna be guaranteed because it's at our supply. Alright, so our biasing is kind of inherently taken care of. You may kind of wonder now, if our collector sits at DC for its, its bias point. Sorry, our collector's DC point is VCC. If we have a signal that gets amplified, we're gonna go above and below VCC, right? Doesn't that feel kind of weird to go above VCC? Going below is fine, we've always been below, but like going above, that feels kind of weird. This is allowed to a certain extent. Obviously, if it's way too large, you're gonna break the transistor. So this is where looking into your maximum CE spec on a transistor is important, because if you're gonna use it for an amplifier in this situation, you gotta make sure this voltage doesn't go too high, at which point get a better transistor, if you're very keen on using this topology. So our signal does go above and below VCC, because we're biased at VCC, and we expect it to be symmetrical because it is an RF signal. Sinusoidal, so power 0. Okay, so there's that. The other thing that's a bit trickier to see is, okay, let me write out one equation here. Generally, for any system, we can construct this equation where big GM I out over V in. This is something I guess you'd probably talk about in 115B, I suppose. But this equation always holds. And I'm gonna talk about some more next lecture and some nuances, and although it's very useful, it hides some of the detail away that you might not see. But we look at this equation directly. Before we have, R naught parallel RC parallel RL, that's your R out. And then now it's just R naught parallel with RLP. So R out increases, so we can see, okay, our gain is gonna increase from this proportionality here. Our GM also increases slightly because we have an inductor to bias. It's a bit weird to think about. You can go through all the math if you'd like, or I can find a derivation later and post it. But effectively, the fact that we have no voltage drop from supply to collector means we, in a way, get more current, which means our GM is basically how much current we get for a certain input voltage. So we get more current, GM is a bit larger, so we end up both kind of increasing, gain goes higher. End of the day, we can never beat this. That's always there. But we can try to get as close to it as possible, and that's the goal. Now this is it's a normal system. It's not a microwave system. We're not talking about reflections here per se. But next lecture we'll talk about if we did. And even if we don't have reflections, we can still use certain design procedures to make sure that we squeeze as much gain out in these transistors as possible. And if you like, I guess more of this, we'll talk about this next lecture, but S parameters, wrap returners, a few of you are interested in, it'd be a very interesting thing to explore because that's all ADS, it's all microwave systems, and wrap is 27 megahertz. Our board is, I would drop to scale, that's too big. If I draw to scale, it's like this. At 27 megahertz, you're not going to really see any appreciable, RF things going on here. KVL still holds, it's pretty much the time depends on someone's spatial. So we don't notice these things going on. It still helps to design around these things because it's important to be aware. And as a good designer, you should be aware of a lot of the pitfalls of the situation you're in. Wrap returners dives into all of this a bit more. And if you talk, at least the amplifiers we do there, and in wrap that we're going to be designing, it's going to look like this, but a bit more complicated. And the reason for that is we're going to have some more additional networks here and here at the input for certain reasons. And I guess I have a few more minutes so I can quickly talk about why. You may think this is perfect, it's great. However,
I just wanted to ask, is there a reason why we're doing an LC tank as opposed to like a current source?
to bias it, you mean?
Or bias it to because then we would have our own parallel, like our
Oh, you mean like an active load type of thing?
yeah.
Yeah, you can very well do an active load too. However, right, your gains is going to be negative GM R naught N parallel R naught P, right? And of course, it's typically just going to be half of your GM R naught N, roughly. And why get half when we can make this pretty large? Again, Q is like 10 and RS is like 50.
That's just that like we typically don't like conductors.
Yeah.
That's what I was like.
We typically don't like inductors, but for this reason, well, we do like them because they create a very sharp. If you look at the impedance at our collector, very sharp response, and we like having this because all of the frequencies we don't amplify. And when this is going to touch on what I was just saying is that when we make amplifiers, it's very easy to accidentally make an oscillator. You may think that's kind of weird at first because, okay, for an oscillator, we talked about before, we have a Colpitts oscillator. You know, we're gonna have some like feedback from here going back into our input, right? But do we see any feedback there? You can argue that RE and CE is a type of feedback, which it is, but that will never cause oscillation here. What does is our PCB trace, right? Parasitics, from our contacts, we can have, that's the best way of describing this. We operate on a physical board. If there's a signal here, some of it might be seen here, just because we have a physical trace. Let me take that back. We have physical material here. The trace is already contacts, it's wires. But even though there's no direct path for conduction, you can still see some effects. Is that very noticeable here, these frequencies? Not really. But higher frequencies, it's very easy to accidentally make an oscillator. The common joke is, you make an amplifier, you get an oscillator, you make an oscillator, you can't get to the oscillator, so it just becomes an amplifier. That happens all the time. And basically, if you have this phenomena, other frequencies get attenuated. Other frequencies get attenuated enough, they can't oscillate. Can't oscillate at those frequencies, right? So that's the idea here. And I guess, you see this in LNAs as well. That way, you can greatly limit other frequencies that come in, out of band frequencies. That for that reason, for oscillation, for general saturation, as well as for noise performance. We'll talk a bit more about that maybe next time. I don't know if I want to have an actual LNA lecture or just have you guys come to the lab one day and I just scribble things onto a board. We'll see. But I think LNA stuff is pretty cool, and I wouldn't say it's like a capstone, but it kind of makes you think about all the different concepts so far and put them together. Active loads and I guess like cascodes are probably something you could do for amplifiers. For rap, is it necessarily worth it? I don't think so. It's something that would be interesting, but it's also a lot harder to teach. And that's the reason why we just have very simple, common emitter stages, Class A amplifiers. Yeah.
Are there other amplifiers that just amplify one certain frequency? Because like,
by default, no. I mean, you need to have CE or an inductor there. Because the whole point of an amplifier is ideally you don't. The frequency response is going to kind of stay the same. When we talk about a transistor, right? You have like your FT. So at some point you're going to start to see your gain start to roll off, and you can't just have your gain look something like that, So when we want to make things roll off sooner, for your FT, you add more capacitance, shrinks it down. If you want a characteristic like this, your transistor does not naturally provide this. Why? Because if you think about it, this looks inductive, this looks capacitive. Is your transistor ever look inductive? Not really. You can make like an active inductor using a transistor, but that requires you to bias it in a certain way, at which point it's not really the same thing. So when you talk about that, yeah, there's no such like amplifier that's just a transistor by itself that'll have this response. You need to have external things in the signal path, in the bias path, to make sure you get some response that looks like this. Yeah, I mean, I guess you can make a general wideband amplifier and just shove it through like a resonator or something, but no, not the same thing.
you mentioned you can make an inductor out of a transistor.
Yeah, it's not really something that's commonly done anywhere. Professor Tom Lee of Stanford wrote a paper on that, but basically, I'll draw the MOS version. This is not rap related anymore. Things like this. And if you look at the frequency response, it kind of, how do I explain this? If you look at it, it's resistance impedance here. You get like a characteristic that kind of increases like this, eventually flattens out, and it looks inductive here. Similarly, you can have something where it's like some other topology where it looks like capacitive, so it's gonna go down. Something looks like this maybe, looks capacitive here. As for why they're used, or rather not used, I don't know. I was gonna ask Professor Wasabi about that. Because the only place it makes sense to use them is for ICs. And if I had to guess, it would be PVT variations, quality factor variations, limited inductor values. You have to bias it in a certain regime. But PVT and quality factor would be my main two guesses. Yeah. Anything else? Yeah. Active inductors are kind of interesting. I know they are definitely used, but not very often.
I think I've seen something like that used in like really sharp filters. But instead of like just like U2, they used like a bunch of, it was for discrete filters, like with op amps, active op amp filters.
Oh yeah.
It's like fundamentally they're modeling it as like an inductor. It's just you know.
That's a bit. Yeah, so you're talking about. You mean like active filter as far as like you have an integrator? Yeah, so it's not like you're using it as an inductor, more so to take the value of an inductor. That makes any sense.
Yeah,
There's
yeah,
also
no,
like
it's not the. I know what you mean.
Yeah.
But yeah.
The closest thing to that would be like sharp filters, like as crystals in a way. You know, you can use as like in a, for this, right? They'll resonate at a certain place, have really high Q. You can use those for filters. You can even use that here if you'd like. The problem is you would need a crystal that has like 3 terminals rather, sorry. It's gonna be kind of weird because you need to have it connected to supply, you need to have it connected to collector and to your next stage. You might be able to find something, but yeah.
There's a paper by Wasabi on active inductors.
Yeah. There's one by Professor Tom Lee as well. That was a really big thing for his PhD, I think. Alright, so no other questions, yeah? Cool. I'm gonna drop the module sometime tomorrow. Try and work on it as soon as you can. Again, it's not like a mandatory thing, but just help you explore the concepts. Because now that we've put the whole system together pretty